Hello everybody, welcome to the Physics Corner. This is a series of videos in which we show how to solve interesting and introductory physics problems. I'm your host, Dr. Christopher Sorolla. Today we're looking at another static electricity problem, this time at point charges. So what are the forces between point charges of electricity, and more to the point, how would you combine them if you have more than, say, two charges? Well, it's similar to how you might have worked force problems in the past, in that forces exist between pairs of objects. And that's what we're going to do here. We're going to take a look at pairs of objects, find the force acting on one of those objects, then take a look at another pair of objects, find the force between those pair of objects, and go from there. Second thing, if you remember about forces, is that forces, F equals ma specifically, Newton's second law, applies to one object at a time. So that's what we're going to try. So here's the particular setup. Imagine we have three different charges located in a position like this. So we have charge QZ here, charge QN here, and charge QJ here. By the way, let's imagine, for example, that these are three siblings with the random names of Zachary, Natalie, and Joshua. And so brothers and sister. And they're busy fighting or having some sort of tug of war over some particular toy. Or, in this particular case, the tugging is because of electrical forces. So our question is this. Let's imagine what's happening to charge Natalie, QN, right here. So what we need to do then is find the force between QZ and QN, find the force between QJ and QN, and then, if we wish to, combine the two sets of forces together to create an overall force acting on Natalie at the origin. So that's why we put Natalie at the origin, by the way. It's kind of a good point here. So we could do this for Zach and Josh charges as well, right? But that is a different setup. So let's do this one and see how you work it. So like I said before, when we apply forces, first off, F equals ma, and that means we apply to one object at a time. Second thing is, if we want to find the forces acting on one particular object, well, that's one object acting on another. Let's keep that one object in common. Let me show you. So first off, let's find the forces acting between QZ and QN. Now, I've given you some starting information here. So let's imagine that the charge on Z is 5 microcoulombs, which we, by the way, we can write like this. This little mu sign here is the prefix for micro. For Natalie, it's a negative 5 microcoulombs. And for Joshua, it is a positive 10 microcoulombs. Now, I've kind of written out an exponential form because that's how we actually have to do the calculation. But it's worth noting that this is a shorthand version of it. Okay, so back to Zach and Natalie. Here's Zach, here's Natalie. What's the force acting on Natalie because of Zachary's presence? Also, we do need some dimensions here. So let's imagine this distance is 0.5 meters. And we'll set this distance as well. That's 1 meter there. So we have distances and we have charges. All right, let's try it. So between Zachary and Natalie, to keep this distinct from the other forces we might encounter, let's call this force of Zach acting on Natalie, like that, FZN. Now, the only reason to use the subscripts is exactly for this purpose. It's to distinguish between any other forces we might have in the problem. So that's what subscripts are for in the first place, right? It's to distinguish similar quantities, but not the same actual specific items, right? So what is this force then? Well, the formula for force between individual point charges is KQ1 Q2 over R squared. Well, as always, let's adapt this specific equation to our circumstance. So K is a constant, so that remains the same. Q1, we'll call that QZ. Q2 we'll call QN. And then the distance between them would be RZN. And of course, that is squared like that. Okay. And again, the point of doing it like this is to distinguish between all possible permutations, you will, of charges and distances and forces. It sounds like we're adding a little bit of extra stuff to do this, but it's worth it because it keeps us centered. It keeps us focused on the specific items we need to play with at that time. And we don't get mixed up with others. All right, let's put in some numbers. Now, just to save us some time, I'm not going to write the units in this particular case, but we do have the units stated up here. So The electrical constant, rounded off, is 9 times 10 to the positive power 9, like that. Notice it's in newtons times meters squared per coulomb squared. Okay, charge of Zach, 5 times 10 to the negative 6 coulombs. Charge of Natalie is a negative 5 times 10 to the negative 6 coulombs as well. And then the distance is 0.5 meters squared. Now, if you look carefully at the units, which I didn't draw in, but let's consider them. This charge on Zach is coulombs. The charge on Natalie is coulombs. That's coulomb squared. That would cancel the divided by coulomb squared in the K. This here, the 0.5 in the bottom squared, that's meters squared. That will cancel with the meters on top in the constant K, and we will be left with newtons. So if we do this, we'll be good. If we put in the microcoulombs instead, we would get the right kind of number out front, but our exponents will be all messed up, and we don't want that. Okay, this one actually is fairly simple as far as the calculator is concerned. When all is said and done, the force between Zach and Natalie is 0.9 newtons. Now, next question is, what's the direction of the force? Now, I could use the negative sign here and put it there, but that's a little misleading. The negative sign, remember, tells us what? It tells us that the force is attractive. So, remember how this works for electricity. If you have two charges that have the same sign, you'll get a positive sign when you multiply those together, right? Positive multiplied by positive, of course, is positive. Negative multiplied by negative is also positive. And that means repulsive force. If, on the other hand, you have a negative multiplied by a positive, and it doesn't matter which direction you do that in, then, or which order, then you get a negative force that's attractive force. So this means Zach will be exerting an attractive force on Natalie. In the picture, that means Zach is going to exert a force pulling Natalie up like that. So we can leave the positive sign alone here in terms of the picture. If we have, as our usual sort of standard way of doing things, positive y going up and a positive x to the right, then this is a force acting in the positive y direction, and we can leave it there. So let's go ahead and just simply state that. And that's the answer for Zach and Natalie. All right, since we've done this, let's go ahead and check out Josh versus Natalie as well. So here's Josh, and here's Natalie there. Force between Josh and Natalie then is KQJQN. Again, it doesn't matter which order you multiply these. And divided by the distance between Josh and Natalie squared like that. So same logic, basically. Notice now this is why we introduced all these subscripts. This charge QZ is not the same as this charge QJ. This distance RZN is not the same distance as RJN. They're different, so we have to distinguish them somehow. So you could skip this in your problems if you wish, but doing it this way helps us keep track of everything. Okay. Let's write out the numbers, just to have them written out. So 9 times 10 to the positive 9. Josh charge, J charge, is 10 times 10 to the minus 6. And it's just fine to leave it as 10 times 10 to the minus 6. You could say 1 times 10 to the minus 5, you'd be fine. And Natalie was again in negative 5 times 10 to the minus 6. This case, I made the distance easy. That's 1 meter squared, so 1 squared on the bottom like that. And when you do this particular calculation, FJN equals 0.45 newtons. All right. Now, again, negative sign we have here, so there's an attractive force between Josh and Natalie. And that means that direction of that force will be something like this. Okay. Also, notice something interesting that pops out of this. The force that Zach exerts on Natalie is larger than the force that Josh exerted on Natalie, even though Zachary's charge was less. In fact, Josh had twice as much charge as Zach, so what gives? Why? Because there's another part of it, there's the distance. Zach was twice as close, if you will, as Josh was, and because distance goes as squared in the formula, it's a little bit more important. So basically you end up with a picture, if you want to draw it out, that looks like this. We have force from Zach on Natalie going up like this, and we have a vector that's half as long. Force of Josh on Natalie would look like that. Now, if you want to take this an extra step further, and that's up to you, I'm going to leave it here. What you could do then is simply, we've got the makings of a right triangle waiting to happen. We've got an adjacent side and an opposite side. You can use Pythagorean theorem and your trig functions to determine angles and magnitudes of the overall force. One last comment before we go. Notice what we didn't do. We did not calculate the force between Zach and Josh. Well, first question, is there one? The answer is yes, there is in the picture. They both have charges and they both have a distance between them. Therefore, there is a force that's being exerted on either of them. But that was not the question. The question was, what is the force acting on the charge at the origin, Qn? And that's why we set it up as Qn here and here. Notice that the Natalie charge was common to both of those calculations. Right? And that's why we did that way. All right, everybody. That concludes this particular question. So, technical support comes from our good friends Sydney Gouchow and Sophia Turner. Support monetarily is from the University of Mississippi and University of Southern Mississippi. We film these videos in Hattiesburg, Mississippi. I'm your host, Dr. Christopher Sorolla, thanking you as always for your attention and clear skies.